We present an automatic method for creating 3D models of botanical trees developed in dynamically changing wind fields. Our method captures high-frequency oscillations as well as long-term structural adaptations of the branching structure. Input to our method are the parameters of the developmental model and the scene definition. Wind is simulated using smoothed particle hydrodynamics, while the tree environmental response is calculated from temporal integration of tree stress. Our developmental model provides a wide variety of trees and allows for animations of growth in real time. The stress response of a tree is calculated from the wind field and a force model for the branch dynamics. The tree model reacts to forces manually applied by the user as well as to forces caused by dynamically changing wind fields in our system. We couple the wind simulation with the tree model by distributing sensor particles to the branching structure. Using our framework, we can combine physically plausible simulations of wind with an evolved force model for the branch dynamics. This allows us to capture a variety of parameters to guide the growth process. In contrast to static vector fields or noise-based approaches, particle-driven fluid dynamics support precise collision detection of individual tree models and even single branches. Our system supports a two-way coupling of tree models and wind fields, and thereby enables the modelling of important botanical effects that have been neglected so far. The framework handles collisions with obstacles and automatically adapts to changes in the environment. A wide range of user interaction is supported. In this sequence, the user interacts with the framework by initiating or directly modifying the wind field. A user can interactively influence the developmental process. The system allows for adjustments to the environment while the tree stabilizes its branching structure. We achieve this by sampling the wind field for a period of time. The development solidifies the branches and the tree becomes more and more rigid. The younger branches of a given developmental state remain flexible and slowly adjust according to the prevailing wind direction. Our system supports the breaking of branches when the stress on the branching structure exceeds a certain threshold. Due to a precise collision response of branches, even more complex phenomena, such as the abrasion and the drying of buds, can be modelled in our framework. We evaluated our method by comparing the sway motions and frequency spectra to real-world data, similar to the approach discussed in James et al. As can be seen, our method is in tune with the natural sway characteristics of trees. In this sequence, we see the motion path of a single particle tracked for a period of 2 minutes. These results were generated by using our framework. We can animate fully developed, highly complex tree models. The models react to abrupt variations in the wind field, while at the same time stabilizing their structure according to the prevailing wind direction. A large variety of different species can be modelled using our framework. Environmental effects, such as the abrasion of buds and the breaking of branches, allow a more realistic modelling of trees. This sequence shows a group of pine trees processed with our system. As can be seen, the models suffer from a variety of effects caused by a wind field. Our method enables wind-tree interaction to be simulated for complex scenes. Even though this is not real time, our system allows plausible scenes to be modelled at interactive rates.